In previous lecture, we modeled series and parallel RLC circuits which produced second-order differential equation and then observed the response of such circuits with zero input. The zero input response was due to the initial conditions of energy storage elements, inductor and capacitor, which were plugged into the circuit at any time t equal to 0. In today's lecture, we will be discussing about the natural, that is the zero input response, along with the forced response of such circuits, so that we can find the behavior of these circuits with time. The basic difference between natural and forced response is that in natural response the input is made equal to 0, whereas in forced response the input is kept as it is and is not made equal to 0. Today, we first obtain a general form of zero input response of the circuit, also called the natural response of the circuit. The second order differential equation with a zero input is of the form this, where A2, A1 and A0 are the constants. The solution of this equation produces a zero input response, or also called the natural response. That's why Y has a subscript n, where n stands for natural. Dividing both sides of equation by A2, we get this equation. This equation can be written in general form in terms of zeta and omega naught as this, where we have put A1 over A2 equal to 2 zeta omega naught and A0 over A2 equal to omega naught square. Writing the differential equation in terms of omega naught and zeta is important in characterizing the system. The parameter omega naught is called undamped natural frequency and zeta is called the damping ratio. We'll do an example to highlight the importance of writing differential equation in terms of omega naught and zeta as follows. For an example, we are given with a series RLC circuit and are asked to determine the parameters such as undamped natural frequency, omega naught, and damping ratio, zeta, of a series RLC circuit. Now we know that for a series RLC circuit, we have previously derived the equation in terms of voltage across capacitor, VC, which is this one. In this equation, in order to find the natural response, that is the zero input response, we put Vthevenin equal to 0. Then dividing both sides by LC, we get the second order differential equation in standard form, which can then be compared with this equation. Therefore, omega naught square is equal to 1 over LC and 2 zeta omega naught is equal to RT over L. Now, putting the values, we get omega naught square equal to 1 over L, which is 1 millihenry, and C, which is 1 microfarad, and thus the value of omega naught is equal to 31622 radian per second. Similarly, the value of zeta, the damping ratio, is evaluated as RT over L times 2 times omega naught, which becomes 2 kilo ohm divided by 1 millihenry times 2 times 31622, the value of omega naught already obtained, and is equal to 31. Note that in order to find the values of omega naught and zeta, we don't need to know the value of input voltage applied to the circuit, because input voltage is made equal to 0 in order to find the value of zeta and omega naught. Once a standard form of natural response, that is the zero input response of the circuit, is obtained, we can solve it using the same method as was used previously in order to solve a second order differential equation. We assume that yn is equal to k e raised to the power st and put it in this equation. Therefore, we get this equation. Now, e raised to the power st cannot be equal to 0 for all t, and k cannot be equal to 0 as well. So we get the characteristic equation as this. Now, solving this equation by use of quadratic formula, we get the root of the characteristic equation shown here. Once the roots of the characteristic equation are obtained, we can see that if the discriminant is greater than 0, that is zeta square minus 1 is greater than 0, then we can get real and distinct roots. When zeta square minus 1 is greater than 0, it means that zeta will be greater than 1. If the roots of the characteristic equation are real and distinct, we know that the solution is of the form k1 e to the power minus root number 1 times t plus k2 e to the power root number 2 times t. Such a response is called overdamped response. Similarly, if the discriminant zeta square minus 1 is equal to 0, which is only possible when zeta is equal to 1, then the roots are repeated, the response is critically damped, and the solution is of the form k1 e to the power root times t plus k2 t e raised to the power root times t. In case when discriminant zeta square minus 1 is less than 0, which is possible only when zeta is less than 1, then the roots are complex conjugate in the form of minus alpha plus minus j beta, and the response is called underdamped response. The solution in such a case is of the form k1 e to the power real part times t multiplied by cosine of imaginary part times t plus k2 e to the power real part times t multiplied by sine of imaginary part times t. As an example, if we need to identify the response of a series RLC circuit with the circuit elements having values RT equal to 2 kilo ohms and inductor equal to 1 millihenry and capacitor equal to 1 microfarad. We calculate the values of omega naught and zeta in the same way as is done in the previous example. Then since the value of zeta is found as 31, and we know from the previous table obtained that if zeta is greater than 1, it means the response of the system is overdamped. Hence, option A is the correct choice for the given values of circuit elements. Therefore, we can conclude that the general form of second order differential equation in terms of omega naught and zeta is useful in finding whether the response of the system is underdamped, overdamped, or critically damped.